Hello everyone. Uh, good evening, and today is the first session of DSA tools. DSA tools means Dynamic Stability Assessment tools. So it is basically a software which is having multiple different modules to perform different operations or different analysis in power system. So as you can see, this is the website of DSA tools, and as I said, it contains multiple tools. So basically, there are some few tools which we are going to use, and it has very much similarity with PSSE, and the underlying philosophy is more or less the same. Okay, so as we started previously also that let's just start with the example of four machine system given in Power System Stability and Control book by Dr. Prabha Kundur. So let's say we have to understand, we have to analyze that system. So first thing we required, that is power flow or a load flow. Second thing we required is the dynamic stability or time domain simulation of that system. So, and third thing we required is the small signal stability analysis of the system. Okay, so here also we have multiple tools, multiple modules to perform different tasks. So first tool is PSET, which basically basically perform the load flow for us. Then the second part, that is S set, which is used to perform the small signal analysis, and the third part is T set to perform transient stability analysis. Okay, so we'll go one by one. So in our institute at IIT Bombay, we have 4 license key available of this software. Again, this is not a free open source software. This is a proprietary software. So at IIT Bombay, we have purchased 4 licenses. So I am having one key attached to my PC. So let me open the first module, that is PSET, and I'll walk through the different functionality and how to use it. Okay. So this is the first window of the module PSET. Okay, and here what we can do is that as we seen last time, we have in PSSC software, we know that to save the solve load flow, we use the data format called .raw, and the same data file, the same file we can simply use here. So what we have to do, we just have to use import, and here we have to select like that raw file is in which version, that we have to select appropriately, and then we just have to select that raw file. So I have in my system here this Power Machine Kundur book. I uh, i have imported it, and sorry. I'll just take a pause. I'll just pause it here. I'll just join in a minute. Okay. Okay. Yeah. So I forget to add this raw file of version 33. So yes, this is, we have to make sure that we have appropriate file in appropriate version. So again, let's start from there. So again, import, then raw version 33, and this is that file. Import and done. So as you can see here in that project tab, similar to what we have in PSSC, you have all the different data available. Okay, so yeah, so as you have seen in the PSSE, here also the data will be displayed in a tabular form. So let's say, let me open the AC bus. So as you can see, these are the same data which we have in PSSE previously. So you already have the PSSE raw file and all which we have previously said. So you can also try to load it into this pset. Okay, so here also in the same way as PSSE, you can see that we have different option to give the the bus type, then bus base kV, then in per unit as well as in angle. All those data we can give here. Fine. Okay. Another thing is the generator data. So the same way we have seen PSSE, you can enter the generator data, appropriate generator data here. Now all this all those entries what you are seeing, it is similar or same to what we have seen in PSSE. All the data which we are seeing here, it is same or similar to what we have already done in PSSE. But in case if you have any doubt, you can uh, always explore the manual available. So in a help file, in the open manual, yeah. In this manual, you can see the details of all the available options. So let me just take you in one of the option. Here. So let's say in a different model and its properties. So let's see about this AC bus, page number 57. AC bus. So here you can see like number means what its significance, what is the meaning of that, what value to enter there, then base KV, then what value to enter there, equipment name, types, so different type of buses, load bus, generator bus, swing bus, out of service bus, and all other things you can find it, you can find the details here. Same way in a generator as well. How they model the generator, what are the limits which you have to set, what are the options which you have to enable or disable. All those details are given very well in this manual. So one can explore this manual and edit the data as suits. So again, first part, that is data entry part. So I have shown you one way to do it, that is to import from the raw file, that is PSSC compatible raw files. Another thing, you can also in the same way you can enter the data here manually. Same way as we did in a PSSC. Again here in a exactly same way. So let's say there are 11 buses. I want to add 12th bus. So I just have to type 12 and start entering the data. Start entering the appropriate data here. I said it's a PSS only. It looks so similar that I just got confused. So here in AC bus, we have total 11 bus, and we want to add one more bus here. So in the edit, insert new row, and here we can add bus number 12. Let's call it a load bus with a base kV of 230. Yeah, with a base kV of 230 and 1 per unit. And then we can add the load, or we can add the line as well as load, whatever like to add here. The same way we have added in a PSSE. But for a bigger system, it is better if we have the saved row file. Then we can just simply import it and edit it, and then we can see how we can solve the load flow here. So let me just delete this additional bus, and done. Okay, now once we have the data loaded here, we have a different parameters to set to solve the load flow. So in the parameter tab, you can see the solution algorithm. So here we can select Newton-Raphson fast decoupled. That too in a two different ways of doing fast decoupled. So you can choose either of them. Okay, so let's just choose Newton-Raphson, and here you can again set the different load flow parameters like maximum iteration, and then solution tolerance in megawatt or MVAR, or in terms of per unit. So here you can select, unselect, or give appropriate parameters to do the load flow. And in the solution, once you hit the solve, it will solve the load flow. It will give you the summary here. Let me just zoom it out again. It will give you the summary that it's solved, and this is the in two iteration. It's solved in two iteration, and the largest mismatch observed at these two buses. I mean, in largest mismatch in P and largest mismatch in Q, which is almost zero. It means we reach the solution. And same thing you can see here also. Just double tap it. Let's say in a generator. You can see the MVR output, which is similar to what we have seen in PSSE. So this one can confirm that it is actually coming out to be the same. Yeah. So this is it for this PSET module. So again, let me just go through the all the steps. So first, data entry. So if you have already saved the raw file, you can just simply import it using the file import option, or you can make a new file and keep on adding the data here. Third option is to save this PSSE to save the load flow data in the native PSET format. So that is so let's do that. So in a file, save project. So the native is .star.psp. So let's give some name. For machine data. Save. Yeah. So this is if you can see it, PS dot PFB and dot PSP. These two files are native pset files, which is a binary file and which can only be open in pset only. Okay. So later we can save it in this form and we can use it. We can use this as well. Once we enter the data, we have option to select or choose or edit the parameters here to perform the load flow, and then we just have to click on a solve load flow, and then it will just simply solve the load flow and gives us the output. Okay. Here we also have option to get different reports, solution reports. So what about the bus mismatches? What about the bus flow? So here we can see all the bus flow, like from which bus to which bus and how much megawatt is flowing, how much MVR is flowing, what are the total MVA rating of the total power flow, and all those things, all the reports we can see here. We can later save it in any anywhere which accept this tabular data. Okay. Then there are some DC converters, DC flow. So those things also we can report. So this is one very useful thing, just to verify, cross verify that whether is any line is violating the limit, or the flow is above the limit. All those things we can verify from this solution reports. Okay. So yeah, so this is done for the load flow part. I'm assuming that you all are aware about this how to solve the load flow in PSSC. So this is similar to that, and one can just cross check it, cross verify it, and with a different setting, one can just try it. I mean later. Okay. So this is done for PSET. Now we'll go for TSET, means to have the time domain simulation of this system. Okay. Okay. So this is the basic window, opening window of the TSET. And here, I mean, when we in PSSE, if you recall, then to perform the dynamic simulation, what are the steps we took? We first add the network data, then we solve the load flow, then we have converted the loads. Once we have converted the loads, then we add the dynamic data, and then we simulate the system. Then only we have simulated the system. So here also we have to enter those data. So what data is required? Two data files are mandatory. One is data file, I mean the network data file, that is load flow file. Second is dynamic data file. So we'll see how to do it. So let's start from the scratch. So we'll open a new case. This is a case wizard, and here we have to one by one select or give the location of each and every mandatory files. Okay. So here you are seeing like multiple options, multiple tabs are open to enter the location of different files. Some of the files are mandatory, means we have to provide those files, and some of the files are optional, means if we want some other functionality than just a plain simulation, then we have to enter the appropriate optional data to perform those studies. Okay. So let's just right now we'll go with the very basic and we'll only enter the mandatory data only. So first we have to enter the power flow data. So power flow data can be entered in multiple formats. So we can enter directly the raw file, or we can have the native pset file as well. We can add the native pset file as well. So let's just first go with the raw file, and then we'll also see by adding the native pset file. Okay. Okay, done. So we have given data location of power flow file. Next, again it's a mandatory data, which is dynamic data file. So that dynamic data file again we can give in PSSC format, means that .dir file, We can also give the PSLF file, that software which was that's a G software. Then BPA is also another software, so it can accept the file in that format as well, or it also has its native file. So right now, so let's just see with the psse.dyr file. So this is that file. One and done. Next, mandatory data, that is monitoring data. Now here, if you recall in PSSE, to monitor certain parameters or certain outputs, we have set their channel, that is called channel setup wizard in PSSE. Here we have monitor data file tab. So here we have to create now, because we don't have any file readily available, so we have to create. So it extract, or it parse the raw file which we have given, and now it will give us all the generator, bus, load, all the tabs is available here. We just have to click, let's say, add generator 1 2 3 4, add it here, okay, and done. So now we can monitor, we can save the data of this 4 generator. Let's call about bus, so we can add, can select all, add, and okay. So now we are monitoring all the buses as well. Okay, and if we want some additional quantity to be monitored, we can just select it. Let's say voltage frequency rate, that is rock off. In generator also we can give, let's say, a rotor angle only, or standard output, which includes all the basic output of a generator, as well as this additional output we can select if we require, if you want to have it. Okay, so let's just save it, this basic thing. Okay, we have to save it to some name. So let's say monitor. Done. That is also mandatory data. This is also mandatory data, so we have to give it. Now next, contingency data, contingency file. So to perform a time domain simulation, we have to give a set of instructions, such as what to simulate. Let's say if we want to simulate a fault case, then when to give the fault, where to give the fault, a fault at what magnitude. I mean, is it a bolted fault, or a fault via an impedance, or all those the settings we have to give. All the settings we have to give in a file. All the sequences we have to give in a file. And when we actually simulate, it will just follow the steps which we used to give here. Okay, so here this file also we have to create some mandatory data we have to create. So we'll create 2 sequences. The first sequence, that is base case, no fault, nothing, just plain simulation for 10 seconds. And second case, where we actually want to simulate a fault. Okay, so in a create customize contingency using contingency editor. Okay, here we have to give the description. So let's the first call base simulation of 10 seconds. Then in the add tab, now in 10 seconds, if we do not add anything, then it will take the default values. Default value means to do and to perform any simulation, what default value is required, that is what is the time step and what is the numerical integration method. Those 2 are we have to give. So right now there is some default parameters to it, default values to it, but we can change it. We can give whatever the settings or whatever the parameters we like to give. So let's just give some time step and integration method here, and then we'll see what are the default value as well. So in the add, in the simulation, you see here we have the option called step size. In the add, in the simulation, step size. So here again 2 options: integration step size in terms of cycles or in terms of seconds. Fine. So let's just keep it in terms of cycles. So or say in terms of seconds. So we want to simulate at 5 milliseconds. So 0.005. Okay, so this is our simulation time step. Then we will add integration method as well, numerical integration method. So it has these 5 options: Runge-Kutta fourth order, trapezoidal, then Runge-Kutta third order, second order, and modified Euler. So for the time being, let's select trapezoidal rule for the numerical integration. Okay, and that's all. We don't want to give any fault, anything, nothing. Just plain simulation for 10 seconds with this time step, and we want to do it with the trapezoidal integration method. Okay. Okay. So done. Our first contingency. Now we want to add second contingency. So that is add. Now this time we want to have a fault. This simulation is also 10 seconds. Again, we'll set the same time steps, same integration method. So step size is 5 millisecond, and integration is trapezoidal. Via integration method is trapezoidal. Now we want to give fault at bus 5 at 1 second. So that is at 1 second. So in a simulation at time, you see at time 1, time of event occurrence 1 second, at time 1, you see at time 1. Now at time 1 second, what we like to do, we like to add a fault. So in a fault, we like to add a 3-phase fault at bus. At bus, we can search it, bus number 5. This is bus number, this is bus name, so bus number 5. Okay, done. So at time 1 second, 3-phase fault at bus 5. Now we want to have it for 100 millisecond, and we want to clear it after 100 millisecond. Okay, self-clearing fault. So again, simulation at time 1.1. Let's just clear in the fault, clear 3-phase fault. Clear 3-phase fault. Done. So this is the sequence. We want to simulate using the time step of 5 millisecond, integration method of trapezoidal. We want to give a fault at 1 second at bus number 5, and at 1.1 second the fault will clear, and done. Then let the simulation be let the simulation go till 10 seconds. Okay. Okay. So now base case, fault case, 2 contingencies. Okay. Again, we have to save this file. So let's just call it sequence data, or let's say fault data. Fine. So this is that contingency file. Now next, this is optional file. So we are not looking into it right now. Again, all this is optional file. All those files are important if you want to perform a different kind of analysis. And in the manual, I'll just show you in a short time that what are the options available, what kind of file, what kind of data we have to give here, and what kind of analysis we can perform with those data. But right now, we'll go with the plain simulation. So we do not require any of this optional data. And done. So we are almost about to save, but before going to save, let's just see the default parameters. So in the parameters, now before going into save, you can see all the files which we have given so far. So this is power flow file, this is dynamic data, this is monitor data, this is contingency data. You can again modify it, edit it, create new file, or search for the file location. Okay, now in the parameter, let's go into parameter setting. Security criteria, we will do transient, we want to do transient stability. Now in a simulation control, as you see, the default one is RK2, Runge-Kutta second order, that's the default one. Okay. And we can also give the default simulation length and simulation step size, and this, if we give some values here, it will override those which we have given in the contingency file. Fine. Then Here we have to give the base MVA of our system, common MVA base and common frequency base. Okay, so it's a 50 hertz system, 60 hertz system. So that we have to give here. And there are other parameters. Okay, one important parameters to use it carefully, that is load modeling. So our load, as you recall in the PSSE, before doing the dynamic simulation, we have to convert the load into the zip model. So it could be a constant current, constant power, or constant impedance, or a combination of all those things. So here also we have to give in a similar way. Here we have to enter like how much percentage of load is constant power load, how much percent is constant current load, and how much percentage is constant impedance load. The only thing which we have to make sure is the sum of all three should be 100 only. Fine. So let's make 100% constant impedance load. That is default P model, that is also 100% constant impedance, and Q also 100% constant impedance. Fine. So now let's save it. Case 1. Save and done. So this is the window once you load the data file here in TSET. So let me just zoom it a bit. This is our base scenario. If you double click on it, you will see this menu again. Here you can again change the parameters, power flow data, load flow, dynamic data. Again, all those data you can see, you can edit, you can create new, you can browse for the file and all. Okay. So in this corner,
फॉल्ट वाला वो भी ऐड कर सकते हैं.
yes, this okay. So this base scenario is a default name, so we can change this name. We can have multiple scenarios here as well. In this scenario we have two contingencies, so there are the difference between scenarios and contingencies. Okay, so we have added two contingencies in one scenario. We can add multiple scenarios. Okay, and here you can see the computational progress window. Here it will see like if you have given some simulation, then how much percentage is done, and here's a result summary. So if there is some issue with the indexing or issue with the stability and all, it will indicate the message here. So again, let me just zoom it here. So these are the two contingencies, the base case and a fault case. Okay, so we'll see once we simulate it, we'll see what kind of data it will show here. Here we can see the generator rotor angles live. So as it simulates, we can see it live, as well as bus voltage magnitude. This is also we can see live. Okay, and later I will show you like where to see all other parameters and all.
Plots, default plots.
These are default plots. So always you will get these two. You can enable, disable it, but you cannot add anything to it. Edit anything here. That we will see like where to see other things in the result tab. Okay, yeah. So now in a dynamic simulation, where as we already given the contingencies, so we'll directly we can directly go for that contingencies, but we can also give some contingencies here as well. That is, let's say we want to give some step in exciter reference, or some step in prime mover reference. So those settings, those kind of simulations we can perform using this tab, which you are seeing on your screen. That is perform an exciter step response test, or perform a governor step response test, and all those things you can do. You can also have an option to run ePMU simulator. That is, TSET also has a module called ePMU. So it can generate a PMU sequence, and if our system is connected to internet, or if you want to take out those data, we can also use those functionalities. Okay, that is additional functionality. We'll see about it later, but I'm just saying that those options are available. Now, what we want to do, we want to simulate the base case and the fault case. So, to do that, we have to select this run base case analysis, the first one. Fine. So, once we hit that tab, it will simulate. So, this is base case and this is fault case. And done. So as you can see, our system after the fault become unstable from this. Now we'll see in detail, like in terms of data. Now, where to see the other quantities? So here in this tab only, you see these specs you are seeing. Further. This one. This is called view result. We just have to open it. So this is that window, DSA tools output analysis window. Here we have both the contingency data, base and fault, and we have different quantities which we have saved. So we have generator parameters and we have bus quantities, bus frequency rate and all. So all we have to, let's say we want to see for the base case, we want to see the generator speed. So we have to select generator speed in hertz and we have to hit it. So this is that speed, 60 hertz. So it's just a numerical discrepancies here, but it's more or less the flat only. It's the same value. Okay, we can select generator by generator here. One by one generator we can select multiple generators and all those things we can. So here we have this in the plot buffer we have generator angle, generator speed. Now we can also add bus frequency or say bus voltage magnitude. Again we plot it and these are bus voltage magnitudes. Fine. Now if you want to see it, are you able to see it? Okay. Now let's go to the fault contingency. We just have to select a fault contingency here and generator speed during that fault. So this is the generator speed. You see, it is going unstable. Fine. Here, yes.
When you run the base scenario,
Hmm.
add multiple contingency,
Hmm.
and once you run it, so all these specs are same for both contingency.
Yes.
Time, step, and this.
Yes. So we have set the same time step. We have set the same integration method. Only difference is the two case. Like one is just a base, and another we have given a sequence that at 1 second we have created a fault for 0.1 second, it's 100 millisecond.
So whenever you run this scenario,
Hmm.
actually sequentially it will run all the
yes, it sequentially it will run all the scenarios. One more option is there. I'll just show you. So in the contingency data, when we select base and fault, you see here that is called base case analysis, transaction analysis, and both is yes. Okay, it means there are two. Currently, we have performed the base case analysis, and this contingency is added to that base case analysis. If we say no here, it will not simulate it. It will not simulate the base case. It will only simulate the fault case. Okay. So this is since we have selected both here. That is why it selected it ran for both. Okay. What I mean is that this contingency 1 and 2, the both are added in the base case. So that's why it ran both. And here in the output, we can see the result. Now it has some additional functionality. Let's say we have this result, but we want to analyze it. We want to know like what are the frequency content of it and what different frequency it contains and what are the damping of it and all those things. Also, we want to export this data to somewhere else. So those functionalities are also available here. We can just select all or any of those data, and in the data tab, we can just simply export. So in the export, we can export into the .xls file or text file or .ps file or .vbs file. So these are the options available for us to save the data. Okay. Once we have saved the data in .text file, we can load back here for further comparison. Okay, so that is one thing, to save the data. Another thing is very useful thing, that is to analyze the data. We can analyze the data here itself. To do it, let's just select generator 1, and in the tools we have Prony analysis. So once we hit it, it will open this window where we have to select certain parameters to perform the Prony analysis, and it will Prony analysis basically give the different frequency component available in a waveform. Okay, it's a time domain data. If we have the analysis of the time domain data is done by the Prony analysis, and it will eventually give us the frequency component, the different the information about the modes visible in the measurement. Okay. So for this waveform, this blue one and this red one is the fitted curve, which is not fitted very well, because I mean that one can look into the analysis of Prony, what are the limitations, all those things. But for this analysis, let's just select ignore modes with frequency less than 0.1 hertz. Okay. And as we know that we have give a fault at 1 second, so let's just start our window after 1 second. Okay, so let's set 1.3 second. Okay, and recalculate. Now you see here, this blue one is our original one, and this red one are the signal from the Prony analysis. So now what we'll do, we can do select one by one, that and these are the table. I mean, these are the frequency component available in this signal. Okay, so let's just say first one, it is 3.5768 radians per second mode with a damping of 53%. Then is another mode. Then this is also looks like a mode. So one caution here, the analysis, the Prony analysis done here, we cannot edit or change the settings or the different parameters of the Prony analysis or the Prony method. Only option we have here is to select this ignore frequency thing. So this will basically remove the offset, DC offset and all. And then from our judgment, we can see, okay, like this is the mode which looks like an unstable mode in a system. Fine. This is also another mode which is stable one. This is unstable mode. This is a stable mode. Then this is also a stable mode. From the damping we can see. Okay. So all this analysis we can perform. At the end, what I'm trying to say is that once we have the data, you can export it, use any other tool to analyze the data, or you have a Prony analysis module built in here with the T-set. So you can use the same data to analyze the system. Okay. And you can export, you can export this result as well. Okay. Now one can just search on the internet further details about the Prony analysis, what are the limitations, what are the advantages, what are the key points of the Prony and all. I am just showing you showing you that there is an option available here to explore. Okay. Okay, so like that we can see all the appropriate output here and analyze the system basically. So done. So this is the part of a T-set, a very brief overview. That if I'm assuming that you are aware about the PSSC simulation. So again, to do any time domain simulation, we require two data. One is load flow data and another is dynamic data. Those two data are mandatory. And another file we have to give here explicitly to for the monitoring data. Basically to set the variables to plot and to give a sequence of steps to perform different contingencies. Okay, once we have done that, we can just simply run it and have the result here, and we can further analyze, explore, or export the data in any format we want. Okay, so this is it for TSET part. One more interesting thing, if we open it in TSET, in the PowerFlow data, since here we have selected the PSSC raw file, we can select the native PSET file, which we have just sometimes back we have saved. We'll just open it. Done. Now, instead of, I mean, since they are, it looks like a two different software. It's just two different modules rather than software. Two just different windows to perform different tasks. But from here itself, we can invoke the PSET uh, to see or modify the load flow data, that is edit in PSET, and it will open it in PSET. We can edit it here, save it, we can edit it and solve it and save it. So once we save it, it will again available here. Okay, so this is some built-in functionality. In wait, it will take some time to come out of it. Yeah. In the dynamic data also, we can create new dynamic data as well. We can edit, or we can browse the file as well. So let's just go into edit tab. So here you can see, as if you recall that in PSSC we have added the generator data in Genro model. This is the PSSC Genro model, and if we double click it, you can see the data. This is the same data which we have given in PSSC. Okay, so we can edit here as well, or we can edit the .dyr file and load it here. The same data which we have in PSSC, those same data we can have it here as well. Then this is also ESAC4, the exciter model, the same way. All the data available to us. Okay. Yeah. So yes, this is it for TSET module. Now we'll just quickly go through the SSET module. That is the module to do small signal stability analysis. So again, we require the same kind of data, a power flow data and a dynamic data to perform the small signal analysis. Okay, so now what are the options available to us in small signal analysis? What kind of analysis we can perform? We'll just see that. So again, I have created a new file, a new case wizard. Next, create a new scenario. Next, title and all, you can give whatever you like. Let's say case 1 like that, or maybe case 2. Here, here we have to select like what kind of computation we want. So here we have option of complete eigenvalue analysis. Then we have option of single machine infinite bus scan. Means it will take each generator one by one and perform the SMIB test of that generator and give the scan of that generator itself. Okay, only that particular generator. So that we can do for all the generators, or we can do it for a particular generator. Then eigen analysis within frequency and damping range. So if we want to get eigen values with particular frequency and particular damping, that also we can extract. So basically, these are the options available for us, which we want to use to select to further study the eigen analysis of the system. So for this analysis, let's just go with complete eigen analysis. We want all the eigenvalues of the system. So complete eigenvalue analysis. Then next. So it will show like what are the mandatory data and what are the optional data. So these two, power flow file and dynamic file, those two files are mandatory and all other are optional. And here we have to select some parameters. These are the default values. We can increase or we can give the new values here, or we can just keep the default one as well. Okay, so right now here we'll just keep the default one. Here we have to give the power flow data file. So we'll give in a raw file. Okay. Here also you have option of edit in pset. So again, it will invoke the pset and you can edit the load flow data there. Next, dynamic data, again in PSSE format. And now all those are optional data. Finish. Case 2. And you see here, you can see this case 2. That is our scenario. And we want to perform complete eigen analysis of the system. Fine. Now we just have to hit this run analysis button and analysis is done. We can do it multiple times. Done. Now to see the result, we have this option view results. Okay. So it will open the another tab. In the case 2, we just have to again start analysis, and this is all the data available to us. Fine. This is, what kind of data available to us is the system have total of 21 number of modes. This is a complete eigenanalysis, a 21th order system, total 21 eigenvalues. What are the real part of the eigenvalue, imaginary part of the eigenvalue, then frequency, then damping. As we seen in the simulation that it is actually an unstable case. So from the small signal analysis also we can see that there is one mode which is having negative damping, means it is unstable. Now that particular mode is associated with which generator. So if you just double click it, it will give you the mode shape as well. I'm just assuming that you know the basics of eigen analysis, what's the most mode shape and all participant fact, what is the participation factor, what is the mode shape. I'm assuming that you know about it. So it will show the mode shape and what are the states involved with this mode and a participation factor, that which state have higher participation, which state have lower participation. So all those analysis you can done here. Fine. So this is basically an inter-area mode. As you can see, generator 1 and 2 having the mode shape in one side and generator 3 and 4 in another side. So it's like 1 and 2 swinging together against 3 and 4, and this is the inter-area mode. And from the participation factor also we can see that all generators have similar participation. If we can see this another mode, this one, you see generator 2 and 1 is having generator 2 and 1 are in opposite. So generator 1 and 2 are swinging against each other, and participation also we can see that generator 1 and 2 is having highest participation in that mode. So it is basically a local mode in which involving generator 1 and 2. So all this analysis we can perform. We can have this result. We can just compare this result with our time domain simulation. And we can export this result as well. So what we have performed is the complete eigenanalysis, but for a very big system, it may take a longer time. Also, not all the modes are of our interest. So based on our interest, we can give the settings like in a computation that analysis within a frequency and damping range, that we want a frequency between this and this, we want a damping between this and this. So those values we can give here, and it will give the appropriate output. It will just sort, it will just give the output within that range, all the modes within that range only. Okay.
Is this what we call selective eigen?
Selective eigenvalue analysis, correct. This is what we call selective eigenvalue analysis, that a mode, identification of a mode around a frequency or within a frequency, we can also perform that. That is very useful when we have a very big system. So that becomes very easy to track and all. And it has all the functionality to get the participation factor, to get the mode shape, to analyze the system and all. Okay, so this is asset part. So we have gone through basically three modules. Uh, PSET first, that is for power flow solution. Then TSET for time domain transient stability analysis, and the S set for small signal analysis. Okay, so there are other modules as well as, I mean, in the DSA tools there are other modules also which are more like a add-on modules to perform different other studies. So we'll see one of the add-on which is called TRI, TSET RTDS interface, which is basically useful to perform hybrid simulation between TSET and RTDS. We'll see further about it in a upcoming sessions. But I'm just giving you a head start that this is what we are heading towards. Okay, so if you have any doubts, you can. I mean, you are invited for discussion. As I said earlier, in IIT Bombay, here we have 4 purchase license key available to use. So if someone wants to try it out, they can reach out to us and we'll provide the license key to them to use the softwares, to try out the softwares. Okay.